than we have today. And it all happened in a tiny fraction of a second, roughly 10 to the minus 30 seconds. And the universe grows exponentially. And what do I mean by growing exponentially? It means it's very, very fast. How fast? It's so fast that if you can shine a beam of light from one person in that speck, or from one observer in that speck to another observer in the speck, the light will not reach the other person during the inflationary epoch, because the space being created between them is so fast, okay, that light just don't have enough time to reach the other side until after inflation ended. So that's how fast the universe is growing. At the end of the inflation, at about 10 to the minus 35 seconds or 10 to the minus 30 seconds, is something still to be worked out. Almost all the dark energy converted to radiation and particles. And this leads to the hot Big Bang that we talked about earlier. Okay? So, exponential. Well, we know that usually linear growth is 1, 2, 3, 4, 5, 6. Exponential is doubling, 1, 2, 4, 8, 16, 32. And then we know this doubling is very, very fast after, you know, this famous stories are one grain of rice, and then 2, and then 4, and then by the time you end there, the whole China will not have enough rice to fill that doubling. Okay? So that's how essentially means exponential growth. That's how fast it is. So essentially, the inflationary universe scenario tells us that all matter comes from inflation, converting from dark energy to our particles. So the picture is the following. We have a constant dark energy density. Sometimes we call inflationary universe, we call infinite quantum energy. And that leads to the universe exponentially grow. But that energy density stays more or less constant. But the volume grows by huge factor, 10 to the 60, some number like that. And then at the end, those energy will be converted to particles, heat up the universe, and that's hot Big Bang. Okay. So during inflation, space is being created exponentially fast. So this is sometimes called the ultimate free lunch. Okay. Everything comes from nothing. So, well, we have one speck to start from. Where does that speck come from? Well, quantum mechanics tells us things can fluctuate. So you can have absolutely nothing. This is, the next few sentences I say speculative, but completely possible. We start from absolutely nothing, no space. So if no space, no observer, is there time? I think that's a philosophical question. But you can have laws of nature. So a tiny quantum fluctuation produce that little speck. And that speck grows exponentially, create our universe. Is the tiny little speck possible from quantum fluctuation? If you put in the numbers, it's entirely possible. And so this I would call absolutely nothing. But if you're not happy with that, you can say, I don't know where the speck comes from, but once that little speck, inflation takes place. And this is more conservative way of thinking about it. But the difference is just one little speck. Now, so with or without that little speck, essentially everything, all matter as well as space, comes from nothing. Okay? What about energy conservation? That's the first question one wants to ask. If you start from nothing, or one tiny little speck with finite energy density, then our whole universe with all these galaxies, stars. There's lots of energy in our universe. Obviously, we can see. Is energy conservation still hold? That's the first thing we learn in physics. Energy is conserved. And the answer is yes, energy is conserved. If the total energy of our whole universe today is exactly zero. Okay? How is that possible? Well, it's not difficult to think about how is that possible. Think about simple things. First, think about capacitor. We have a positive charge plate, negative charge electric plates, and there's the electric field between them. And you put a test particle, it will move to the right. Okay? And we can store energy in the electric field. Okay? And the energy density essentially proportional to E squared over 2. That's the energy density stored in the electric field, which is something that we know very well. The interesting thing is the opposite charge plates attract. There's attractive force between them because opposite electric charges have an attractive force between them. Now let's go to gravitational field. Gravitational field, you have identical mass, we attract. So same mass attract. Okay. Which is exactly opposite because you have same charge, they repel. But gravity, same mass attract. So as a result, the energy in the gravitational field is negative. So whenever you have mass of energy, there will be some gravitational field around it, and that gravitational field will have negative energy. So you have positive energy from mass, negative energy from gravitational field, and we can convince ourselves that it's very possible that matter plus gravitational field energy add up to exactly zero. So this is certainly possible, and inflationary universe follow all the equation of physics as we know today, and the evolution tells you how it can happen. So this is explaining, you can easily go ahead and convince yourself why gravitational field energy is negative by consider parallel charge electric plates and parallel mass plates for gravity. Okay. So dark energy comes from infinite potential, and essentially means that this is the dark energy, and this dark energy drives inflation, and so there's a field called inflaton at a certain point will end when you fall down. Okay? This is the picture that inflationary scenario tell us. Now, so you can roll classically down, but quantum fluctuation happens. So at different space, the field may fluctuate a little bit differently. So they all will classically fall down, but that little fluctuation means that some places will fall down earlier than other places. The place that fall down first will generate heat, and then particles, and that will expand, and the temperature will cool down a little bit before another place fall down and happen. So that will introduce a density fluctuation in different parts of the universe, a temperature difference in different parts of the universe. And that is a clear prediction of this inflationary scenario. Well, so let me summarize. Start from a single point, total energy much less than a single electron, exponential growth from absolute nothing, and produce a size of universe where start the hot Big Bang, and at the end, all the dark energy convert to radiation matter, starting the hot Big Bang, as we just said. And then this end of size and end of inflation, our whole universe at that time has the size more like an apple. Okay? And maybe there's something outside, but that's not observable by us today. So our observable universe have the size more or less like an apple at the end of the inflation rate. So going from 10 to the minus 30 meter to an apple is a huge growth, and that all happened in a tiny little period of time. So we don't know if there's anything outside our observable universe, probably same, more or less, but we don't know, and we cannot detect them at this stage. So this picture is essentially completed by early 1980s. And the question, of course, is a fantastic picture. It's more like science fiction than physics. And for theoretical physicists, it's important to find ways to test these kind of ideas, okay? So that we can convert it to science fiction or philosophy to science. And that's happened precisely because the quantum fluctuation I mentioned during the inflation time that will lead to fluctuation density and temperature. In fact, the density fluctuation is very, very important, because if the whole universe is homogeneous, then it will more or less stay there. Okay? But if you have fluctuation, small fluctuation, then high density region will attract other particles due to gravitational forces. So it will be even higher density. Low density will become lower density. And that's how things start to clump together, cluster, and that's how stars and galaxies get formed. So this density fluctuation is crucial to the large-scale structure of our universe today. The temperature fluctuation, turns out, is also measured by the COBE satellite that measure the blackbody curve I mentioned earlier. And that temperature fluctuation is tiny again. It's 1 part in 100,000. Very tiny. So the temperature, I say, if you look at different directions, you find the temperature is not exactly the same, but they differ by 0.001 degrees, okay, or smaller. But they can measure. That's really, really impressive, that we can measure, the cosmologists, the physicists who build instruments and do measurements can measure 1 part in 100,000 to an accuracy of better than 1%. So this is the universe. These are different temperatures. The blue is light, low temperature. The red is high, the green. And that also causes the density fluctuation. And that's how universe evolved. Okay? This is taken from WMAP website. And you get structure formations and how universe evolved to today's universe because of these fluctuations. Okay? So that means that we can go and have a measure this fluctuation, and the inflationary universe, if it's correct, will tell us what that fluctuation should look like, and we can go and measure to see if it's correct or not. So this is the really amazing thing. So COBE I show is the first one, and then WMAP measure roughly every 10 years, and then more recently Planck did it in 2013. They are all satellites, and of course they're ground-based experiments also. And satellite collecting more data and analyzed more recently, even this year. And we expect more and more data to come in. And the accuracy that can measure is spectacular. That temperature fluctuation, COBE, is like this. The fluctuation Planck can measure, and also today, is much, much more refined. So refined that if you think that this is the surface of the Earth, they can pick up features of the size of maybe an airport. That's how refined it is. And more measurements will come in with better measurements over time. Now, so we can compare the theory and experiment. So you say, if inflation universe happen, what should we see about this fluctuation? And we measure standard wave is in terms of multiples. So multiples of 1 means that more dipole difference. Multiple 2 means that 90 degrees difference, and so on, this multiple wave. And then if they go to 300, it means a 1 degree difference. So that essentially is the angular degree difference measure, and that's the so-called multiples. If you're familiar with partial waves, this is usually the partial wave multiples. And they measure the fluctuation at different scale from the cosmic microwave background radiation that reach us. And the green curve is the theoretical predictions with about 3 parameters. Black body radiation is 1 parameter, so this requires 3, 4 parameters, depends. And the dots are the data. And you can see the inflationary universe prediction is spectacularly in agreement with the data. So this is very, very amazing. And that's why people believe inflationary universe. It solves some outstanding puzzles, but it also gives you very precise predictions, and the precise predictions seem to be borne out by observations. Now, here, low multiples means like you go 90 degrees or you go 180 degrees. Down here, the error bars are large of the data, and also there's some called green. The prediction also is a band, very wide band. And the reason is very simple. If you look at 90 degrees difference, I can look at 90 degrees difference. And I only have 2 data points, since we only have 1 universe to observe. So automatically, there's large error bars. When you go to high multiples, you can many measurements, so the error bars become small. And the reason is because we only have 1 universe, so when experiment done, once we can measure 2 numbers for multiple 2, and so error bars large. This is called cosmic variance. Okay. It's just because of statistics. So with this, and I should also mention that the polarized measurements, other measurements, essentially imply that the inflationary universe is very likely to be the correct theory. Depends, different people you ask. Other people try to find alternatives, which I think is very important. You want to find alternatives to the theory to see if you can make more precise tests of the inflationary scenario. But some people think that it's already proved correct, including like people like Steve Hawking thinks that the data overwhelmingly support the inflationary scenario. Okay. So now, let me go to a slightly different way. If we think that inflationary scenario is correct, and if we think string theory is the theory that describes all particle physics, including gravity, then we must find out how string theory describes inflation, and if there's any other predictions we can make that we can test. Okay. So the simplest scenario now is that string theory is a brane world, because in string theory, besides strings, there are branes. Okay, 2-dimensional branes we call membrane. 3-dimensional, we don't want a new name, so we call 3-brane. And we probably live in a 3-brane, which have 3 spatial dimensions. A membrane have 2 spatial dimensions, so we call 2-brane. And so we may be living in the brane, our whole universe in the brane, but outside universe is extra dimensions that string theory gives us. And in this scenario, we can do something brane inflation. Suppose there's a stack of branes. Today we live in a stack of branes. But early universe, maybe there are extra branes, anti-branes. So before they collide, there's vacuum energy which drives inflation, or we call dark energy, drives inflation. And once they collide, they annihilate and produce a lot of heat, start the hot Big Bang. This is one of the simplest scenarios that you can think about string theory. You can think about other scenarios. In this picture, of course, the universe may have multiverse, and that's another story that I have no time to go into. But if it's correct, then we say everything is made of strings and branes, of course. Some strings are tiny, an electron, a photon, they are tiny little strings, but quarks, neutrino, they each are tiny little strings. But in the early universe, you can produce strings which are long, stretch out, and we consider that as cosmic strings. And they're naturally produced as well. And these cosmic strings should be the size of the universe, can be, or size of a galaxy, or typical size, which range from all sizes. They can have different tensions and spectra because the string theory computation is complicated with wave geometry. So the cosmic strings with large tension will decay rapidly, but cosmic strings with small tension, means the weak gravitational interactions, will decay very slowly, so they may cluster. Now we know dark matter cluster around our galaxies. That is, the dark matter density in our galaxy is probably 5 orders magnitude that of outer space. And that's why we have the rotational curve that indicates the dark matter. Cosmic strings with low tension can also cluster, and then we increase the density by 5 orders magnitude, typically. And then, once there are many of these little strings, they can lead to microlensing. What's microlensing? Well, microlensing is something like this. You have a star out there, and if a cosmic string passes by that star, the luminosity of the star will become a double image, so luminosity becomes double. You cannot resolve it because the distance scale is too small, but what you can see is that this is 0, this is the luminosity luminosity of star, and when the cosmic string passes it, the luminosity will double, and then when it passes it, go back to 0. So a string will oscillate, and you have this, and then when the loop passes by, you may have this. So this digital behavior of a brightness of a star will be very, very clear indication that a cosmic string has passed in front of it. This may be detected in the coming years. The experiments, GAIA, LSST, and others have a chance of detecting such events. We have to wait. But once they see one event, it will be very, very distinctive. Okay? Notice the spectrum photometry of the star won't change, just the double and single. So there are many ways to study the universe. We talk about the satellites, and then ground-based experiments like these gravitational wave detectors, LIGO, and in South Pole they have many, many detectors, ice cube to neutrinos, and then detecting polarized microwave background radiation. So I have not mentioned polarization. The light coming towards us is always, or not light, but microwave coming towards us, coming from the early universe produced. It's linearly polarized. They can be polarized like E mode or B mode. So E mode is like this, B mode is like this. Essentially means that you cannot tell reflection through a mirror, or B mode you can tell. And they have detected E modes, which is a clear indication that cosmic microwave background radiation agrees with the theory, but they have not detected B mode, and inflationary universe also think that they should detect some. And so there's a big effort in searching for the B mode polarization of the cosmic microwave background radiation. A year and a half ago, there's a claim they detected it by a group called BICEP, a group of young, energetic, enthusiastic physicists. Turns out the detection is correct, but it's probably due to dust in the interstellar space. So to find the primordial, that means the B mode produced by the inflationary scenario remains to be detected. And there's many experiments in South Pole, in the Atacama Plateau in Chile, and other places try to detect that. And here I show bicep, but there's a number of experiments there. And people try very hard. And if you like to be isolated for 6 months, you should go and get a job there. So why the B mode polarization is important? The reason is inflation predicts the existence of B mode with a well-defined spectrum, but unfortunately not the magnitude. So alternative to inflation, people propose so far, all have no B modes. So no B modes is consistent with inflation and a couple of alternatives, but detection of B modes from primordial inflationary will sort of rule out the alternatives. So that's why it's very important. It's also coming from the quantum fluctuation of space-time originally. So that's will also be a very important point, which some people think that particles are quantized but not space-time. As I said, there are many experiments going on, and in particular, I list here some. Each one has a contingency of multiple universities, multiple countries collaborating. Much more data will come from. And maybe there will be satellites going up again, next generation, and next generation satellite go up to make a better measurements of what we have. And then there's other ways to test the predictions of inflation by looking at 21 centimeters, distribution of galaxies, etc. So at the beginning of the past century, cosmology is a very speculative field. However, by now, it's very well understood. It's a precision science, and yet there's still many open questions remaining to be further explored and discovered. So, thank you.
Okay, questions?
Thank you for the talk. You said that the energy of mass and the energy of gravitational field will cancel out. How about the black hole?
That's a very good question. So what we know is that if the inflationary scenario is correct, then we start out essentially with no energy, total energy is zero. And so today it must be zero. And since we start with a tiny patch, and we know that the energy density is finite there, times a tiny volume, it's a very, very little. Total energy is less than a mass of electron, single electron. So everything from us must, if inflation is correct, must be added up to exactly zero. And we show how the theory allows us to evolve in a way that happens. And then we show the experimental done that inflationary theory predicts, agree with experiments in a very spectacular way. Okay? So then the only way we know how the total energy today is zero is due to gravitational field cancel them out and energy, the other positive energy. And so now can we count the matter in our universe today and the gravitational field and check that point? That's not something we can do accurately. So the evidence is somewhat indirect, but convincing.
Okay, question here.
How can we tell so is it obvious way to separate the primordial gravitational wave and non-primordial gravitational wave? Suppose like from binary black holes and either from frequencies or from some other ways?
Yeah, the gravitational wave coming from black holes or binary spiraling black holes will be a point source. So if you have enough detectors, you can pinpoint it's a point source. The primordial gravitational wave of fluctuation are primordial everywhere. So that's easy to separate that. And also the spectrum